Swayam Prabha. Digital India. Educated India.
Hello friends, welcome back to this lecture series of BSc with Chemistry, Physical Chemistry Paper 4. This is second lecture of Module 1 wherein we are discussing the conductometry and its other aspects. Friends, in continuation with our previous lecture, we will now see the experimental determination of specific and equivalent conductance. Basically, the conductance of a solution, it can be determined by measuring the resistance offered by a solution contained within two electrodes of conductivity cell. This is particularly the conductivity cell. Now, this specific conductance is determined using the principle of Wheatstone bridge. This is known as Wheatstone bridge. This bridge consists of four arms containing four resistances. Now, when no current flows through the galvanometer, this is particularly the galvanometer, when no current flows through this galvanometer, it means that the potential drop from this B or from this A to the other terminal, from this terminal to this terminal or this terminal to this terminal of the galvanometer, we find out the null point. Now in this technique, the direct current cannot be used because it would cause electrolysis and concentration changes at the electrodes. Now if the gas, if liberated, it will increase the resistance at the polarization which opposes the passage of current. Now to avoid this, alternating current is employed, usually in the frequency range of say 500 to 2000 Hertz. In an alternating current, the direction of the current is reversed about 1000 times per second, with the result that the polarization produced by each pulse of the current is neutralized by the next pulse. Currently, the advanced electronic devices are basically used to determine the null point, and we can use the standard cell for this purpose. Usually there are electronic devices and gadgets which directly gives you which directly calibrates the null point and which directly gives you the conductance null point of the unknown cell, say conductivity cell. But this is the traditional figure which usually used for the understanding of concept. Now if the R is the known resistance box and X is the resistance of the solution at this terminal, you can see over here. So if I take ratio of this R upon X, I get length of OA upon length of OB, isn't it? So the resistance X is equal to resistance R into length of OB upon length of OA, and therefore the conductance will be 1 upon X, and specific conductance will be this kappa is equal to observed conductance into cell constant, that is L upon A, that we have seen, and therefore the equivalent conductance is specific conductance into 1000 upon normality. That way we can calculate this equivalent conductance in Siemens centimeter square per equivalent. This is what is the conventional method or experimental determination of specific and equivalent conductances. In nowadays in many of the laboratories, usually instead of using this traditional method, the potentiometers, electronic devices are used, wherein the standard cells are fitted in the instrument itself, and the user has to only put the connections of the unknown cell, conductivity cell, wherein your solution is put in, and the device displays you directly the conductance, not even resistance. In earlier time we have to measure the resistance, and from the resistance we have to measure the conductance. Let us see some of the basic numericals so as to understand the idea. Say for example, if a cell dipped in 0.1 normal KCl shows the resistance of 120 ohms, calculate the cell constant if specific conductance of 0.1 normal KCl is 1.12 Siemens per meter. So very simple. I have been provided with the specific conductance, resistance is given, so observed conductance is equal to 1 upon R is equal to 1 upon 120, and that is what is observed conductance. So it can be calculated. So once the observed conductance is calculated, I can calculate the cell constant in the following manner. You can substitute the value over here and you can get this particular point. The another example is the resistance of say 0.5 normal solution of an electrolyte is 45 ohms. Calculate equivalent conductance if the electrode of cell are 2.2 centimeter apart and have a cross sectional area of 3.8 centimeter square. Again, a very simple numerical wherein we have been provided with this resistance R, that is 45 ohm. Concentration is given. I can convert it into equivalent per meter cube. Length is given, area of cross section is given. So the observed conductance is nothing but this 1 upon R, and this kappa is equal to observed conductance into cell constant. So if I substitute this value over here, I get the value of specific conductance, and from specific conductance I can calculate the equivalent conductance using this formula. So I get this value of equivalent conductance of 25.72 into 10 to the power minus 4 Siemens meter square per equivalent. Similarly, the one more practice numerical can be done. The resistance of 0.1 molar KCl solution in a conductivity cell is 325 ohm, and the specific conductance of the same solution is 1.29 Siemens per meter. If the resistance of 0.05 molar NaCl solution in the same cell is 752.4 ohms, calculate the equivalent conductance of NaCl solution. See what is given here. We have been provided with the values. Say for KCl solution, this K value is given 1.29 Siemens per meter square, and the specific conductance along with the resistance is provided. So the observed conductance is equal to 1 upon R. So this is observed conductance. We have specific conductance, we have observed conductance. So we can calculate the cell constant, that is 419 per meter. Now once I have with the cell constant, I can actually calculate the observed conductance for NaCl solution. So using this concentration and this resistance, I can calculate the observed conductance is equal to 1 upon R. This is the value which comes out, and therefore the specific conductance is equal to observed conductance into cell constant. So cell constant I know. So observed conductance is 1.329 into 10 to the power minus 3 Siemens into 419 per meter. So my specific conductance is 0.557 Siemens per meter. And once the specific conductance is determined, I can calculate the equivalent conductance using this formula. So this is what is the value for equivalent conductance. These are the simple numericals which we can solve using the concepts that we have assumed. Basically, numericals are very important to understand the concepts. Now, this is one of the very important aspects of the concept of conductance, Kohlrausch law of independent migrations of ions. We will go through this concept in very brief, and we will see its huge applications, number of applications at the end of this lecture series. Okay, for now, what Kohlrausch law of independent migration of ion is, in order to understand, let us say if I consider a strong electrolyte. So for strong electrolyte, the value of molar conductance in a very dilute solution, now how much dilute? Say 0.001 or 0. Even 0.0001 molar solution, it is very close to the limiting value of conductivity at infinite dilution, isn't it? Now on the other hand, the corresponding value for weak electrolyte is far away from the limiting value at zero concentration, because for weak electrolyte it drops down very rapidly at low concentration. Say for example, at 25 degrees centigrade, for say 0.001 molar sodium chloride solution, the molar conductivity is say 123.7 per ohm centimeter square per mole. And whereas if you look at the molar conductance at infinite dilution, will be around 126.5 per ohm centimeter square per mole. At the same time, at the same concentration and temperature, the value for the acetic acid comes out to be 49.2 per ohm centimeter square per mole, as compared to that of 390.7 per ohm centimeter square per mole. So Kohlrausch was the first to observe that when molar conductance for a univalent strong electrolyte like NaCl is plotted against the square root of concentration, the curve approaches linearity in dilute solutions and follows the equation of straight line. Basically, you can see this equation, isn't it? So it follows this equation of straight line where this B is the constant and the value of limiting this value of limiting molar conductance can be obtained by extrapolating the curve to zero concentration. Now this extrapolation method cannot be applied in case of weak electrolyte. Why? We have seen the graph earlier, because the variation of molar conductance with the dilution is very rapid. It drops down very rapidly like this curve, asymptotic curve, isn't it? And therefore, at lower concentration, you cannot find out the intercept. So in such case, for determining the limiting molar conductivities of a weak electrolyte, the Kohlrausch law of independent migration of ion can be employed. That is what is its significance. This law states that the equivalent conductance of any electrolyte at infinite dilution is a sum of equivalent conductance of cation and anion at infinite dilution. Okay. If I want to summarize it in other words, I can say like at infinite dilution where dissociation for all the electrolytes is complete and where all interionic effects disappear, each ion migrates independently of its co-ion and contributes to the total molar conductivity of an electrolyte, uh, which will contribute to a definite share which depends only on its own nature and not at all on the ion with which it is associated. That means, on the basis of this observation, Kohlrausch concluded that each ion makes a definite contribution to the total conductance of electrolyte at infinite dilution. Mathematically, if I want to summarize it, I can summarize it like this. This equivalent conductance or molar conductance at infinite dilution is equal to the summation of equivalent conductance of cation plus equivalent conductance of anion. These are the individual contributions. These are the individual contributions, isn't it? This table summarizes some of the values of molar conductance at infinite dilution for some of the electrolytes like KCl, NaCl, KBr, NaBr. These are the values given, and their differences is given because the effects due to cation and anions, you can see the difference is this much in case of KBr and sodium is this. Likewise, in case of KCl and KBr, it is here. So here in these are anions are in common, cations are in common. You can see the differences in case of cationic ions in common and in case of cationic ions in common, isn't it? Now, one of the very important concept in the field of conductance, that is the theory of Debye-Huckel-Onsager, and this is a theory of ionic atmosphere wherein the ion atmosphere has been studied in detail. We'll try to understand what is ionic atmosphere and how the asymmetric effect and electrophoretic effect are taking place. So now, in many cases of say strong electrolyte, the Ostwald dilution law does not follow. That we have seen. The straight line we do not get a straight line on plotting the Ostwald dilution law. This variation of conductance of strong electrolyte in dilute solution can be explained on the basis of Debye, Huckel, and Onsager theory. According to this theory, each ion in solution is surrounded by the ionic atmosphere. You can see here, isn't it? And this, all of these ions, they are consisting with this ion atmosphere consisting of the other ions having opposite charge. See, this is positive surrounded by negative ions, negative surrounded by positive ions. Okay, and therefore the net average charge is opposite to that of the central ion, isn't it? So this ionic atmosphere is spherical and symmetrical in nature in absence of any disturbing factors such as the application of potential across the two electrode which are immersed in the solution during the conductance measurement. In fact, Onsager was the person who pointed out that as ion move across this solution, the ionic atmosphere gets repeatedly destroyed and formed again. So destroyed and formed, destroyed and formed. This cycles goes on in the solution in absence of any external potential applied to the solution. Now the time usually taken for the formation of new ionic atmosphere is known as the relaxation time. And this relaxation time is usually of the order of say 10 to the power minus 7 seconds or so. However, when the potential is applied, these ions, they start moving towards the respective electrodes, which is very natural. And as a result of the ionic atmosphere of this potential, as a result of this potential and the movement of ions towards the particular electrode, this ionic atmosphere, uniform ionic atmosphere, is distorted. And this distortion results in the decrease in speed of ions. So Debye and Huckel showed that these effects are due to two factors mainly. The first factor is the relaxation of ionic atmosphere due to an applied potential or which is called as asymmetry effect, and the second part is the electrophoretic effect. So if I want to understand the asymmetric effect, what is asymmetric effect? So asymmetry effect is due to the fact that any central ion and its surrounding atmosphere are oppositely charged, and when the central ion is being positively charged, will distort the symmetry of the ionic atmosphere, and which consequently lead to the experience of the opposite direction force when it is moving in one direction. So it will experience the opposite direction force that will slow down its speed. This is one factor. On the other hand, the electrophoretic effect is due to the counter current drag faced by the ion atmosphere. Like if I want to take the example, whenever a swimmer faces the resistance of counter current, whenever the swimmer swims in the opposite direction to the flow of stream, exactly same kind of opposite drag is faced by the ion and its atmosphere. So actually the ion in solutions are generally solvated, and when they move, they carry with them the associated solvent molecules also. So both the types of ions flow with the ion atmosphere. Now while moving in a solution, both these types of ions, they do not travel through the stationary medium, but they travels through the medium which moves in the opposite direction. So a counter current stream is experienced, making it more difficult for the ion to move through the solution, and thus it slows down its motion. This is actually known as electrophoretic effect. Both these effects are pictorially, we have tried to show over here. These are taken from some source mentioned here. This is the asymmetry effect, this drag of to this positive ion, and this is particularly the experience of counter stream to the movement of the ionic cloud and particularly ion, isn't it? Now both these effects are very important, and these are responsible for the effect or slowdown of ionic moment in the solution, isn't it? So those can be quantified also, and Debye, Huckel and Onsager, they have tried to quantify it. We will see it. So the particular drag which was experienced by the due to the asymmetric effect and electrophoretic effect, it can be quantified, and Debye, Huckel and Onsager have given its mathematical expression. So Debye and Huckel showed that both of these effects, like asymmetry and electrophoretic effect of an ion, produces a decrease in molar conductivity, and their mathematical treatment was subsequently extended by Onsager. So particularly Onsager derived this particular equation, this equation number 10, for the molar conductivity of very dilute solution of strong electrolyte. Now this, although it looks like very complicated equation, but this is very simple solution in order to understand. In this particular expression, we will see this particular term, they are associated with individual effects. So if I try to solve this particular two term, and if I would like to specify their origin, it becomes very easier in understanding. Okay, so if I want to see, this is nothing but the equation of straight line. So equivalent molar conductance is equal to molar conductance at infinite dilution minus some constant into square root of concentration, kind of thing is it. Okay, so now if I want to see this Z plus and Z minus are the charge number of on cation and magnitude of charge number on anion respectively, and the epsilon r, which is shown over here, is the relative permittivity of the solvent. C0 is 1 mole per decimeter per dm cube of the concentration, and eta is the viscosity of solvent, and eta 0 is the unit viscosity of this particular solvent, and Q is given as this particular formula. So whatever value of Q, that this Q we have taken over here, it is after solving this particular thing. Okay, so now this lambda plus and lambda minus are limiting ionic conductivities of cation and anion that we have taken, isn't it? These are ionic conductivities which we have taken represented by lambda. So this equation 10 can further be written. So as this particularly of this type, so molar conductance is equal to molar conductance at infinite dilution minus A into molar conductance at infinite dilution plus B. So this we have called as A, this we have called as B. I mean, this quantity multiplied by this quantity is nothing but A, and this quantity multiplied by this quantity is nothing but B, and we have tried to rearrange it. So my first term in this bracket, first term, this particularly A into this quantity, is a decrease in molar conductivity due to asymmetry effect. Okay, and this second term which is shown over here, this is B into this particular quantity, is the decrease in molar conductivity due to electrophoretic effect. This is what is given over here. So as we can see, the first term in equation 12 is decrease in conductivity due to asymmetric effect, and this particularly appearance of this part in this particular expression in the denominator is due to the fact that on increasing my relative permittivity and temperature, the interionic attraction is decreased, which is quite obvious, and therefore there will be less decrease in molar conductivity. Similarly, if I look at the second term, or second term here in equation 12, that is B into this particular quantity, it is the decrease in molar conductivity due to electrophoretic effect. So the appearance of eta in the denominator in this particular term here is due to the fact that the motion of both the atmosphere and the ion is slowed down in a very viscous solvent, and correspondingly the decrease in conductivity will be lesser. So it is very important to note here in equation number 10 that this particular equation number 10 is applicable only to very dilute solutions and may be considered as essentially a limiting equation for conductivity. Or if I consider a special case of say 1:1 electrolyte univalent in water at 25 degrees centigrade, for which usually Z plus or Z minus is equal to 1, and say permittivity is, if I take the value of permittivity is equal to 80 and viscosity is equal to 0.0089 pies, this particular equation number 10 would reduce to this particular expression, the standard expression, equation number 13. Okay, so the comparison of experimental data with the values predicted by the Onsager equation, it reveals that it is in agreement. The agreement is usually excellent in very dilute solutions. And what I mean by dilute solution, these dilute solutions are up to say 0.02 molar. In more concentrated solution, the molar conductivity is usually higher than the value which is predicted from the Onsager equation. So all in all, this particular Onsager equation is valid for only dilute solution, we can say. So this equation gives us the validity of this particular equation for very dilute solution, say up to 0.02 molar. I can take one numerical. Numericals are very best way to understand the concepts, and therefore we have taken the numericals at very regular intervals. Say at 25 degrees centigrade, the constants in the Onsager equation are A is equal to 0.2289 and B is equal to 60.19 Siemens centimeter square per mole. Calculate the molar conductivities of 0.01 molar HCl solution and 0.01 molar KCl solution. Now, given the ionic molar conductivity, limiting ionic molar conductivity is given over here in this fashion. Okay, then notations are given like this. So, the molar conductivity of HCl at infinite dilution is, this is the formula which we know, is it? And if I write down, if I sum it, I get the molar conductance at infinite dilution. Okay, so from ionic conductance I get the molar conductance for HCl, and it is equivalent to this 426.15 Siemens centimeter square per mole. Now the value of molar conductance HCl from Onsager equation, this is the Onsager equation I have. So if I substitute the values, the value of for A is given, then the molar conductance is given, the value of B is given, concentration terms are given, and if I solve this, I get the value of 410.37 Siemens centimeter square per mole. For KCl also I can particularly repeat the same thing. For KCl I can calculate the limiting molar conductance, that is sum of this ionic conductivities 73.52 plus 76.35, it gives me 149.87 Siemens centimeter square per mole. And I can calculate the molar conductance of KCl in this fashion using the Onsager equation. And if I substitute, I get this value of 140.42 Siemens centimeter square per mole. Particularly, one has to take care of the units, and one has to put the values at correct places. So this is how we can utilize this particular concept to solve or utilize the Debye-Heukel Onsager equation. We can utilize this equation to find out the molar conductivities. So friends, we will stop here in this lecture. We will see the other concepts of conductance in our further lectures. Thank you.